Hi everyone, welcome. So we will continue from last time. So as you remember, last time we sort of took a detour and we went to number theory, right? And the reason we did that was because we wanted to construct more advanced primitives like key exchange, public key encryption, and so on. As I said before last time, we cannot do that generically from one-way functions or one-way permutations. At least we don't know how to do that as of now. So we will see some direct constructions of key exchange and public key encryption today. Okay. So let me remind you what the DDH assumption was, which will be very useful for today's lecture. Okay, so DDH assumption was as follows. So you are given g to the power x, g to the power y, g to the power xy, such that x and y are coming from zq. Okay, so G is a generator of some group capital G such that the order of capital G is Q. And the assumption was that this is indistinguishable from G to the power X, G to the power Y. And now we have a random group element, G to the power R. And now X, Y, and R are sampled uniformly, again from ZQ. Right? So essentially it's saying that given g to the power x, g to the power y, computing g to the power xy is so hard that not only you cannot do it, but in fact, even if I gave you the correct solution, you cannot distinguish that from just a random group element. And based on this, today we will look at key exchange, we will look at public key encryption, and so on. So let me start with the problem of key exchange first. So a major limitation of symmetric key encryption or private key encryption is that, let's say I want to send a private message to one of you, then we need to meet first, right? And we need to generate a secret key and we need to exchange it securely. Just the two of us should know the secret key and nobody else. And if we have something like that, then I can encrypt messages and I can start sending encrypted messages to you. But what if we have never met before, right? So let's say I want to send a private message to one of you, right? And let's say I can only basically just communicate over Zoom, no private messages, nothing like that. I can talk, you can talk, all the other students are watching. And we just want to exchange public messages such that at the end, just you and me, we will have the secret key and nobody else would, right? So when you think about it like that, it almost seems impossible, right? Because we didn't have any secret to start with. We only exchanged public messages, which everybody was watching. So if you and I can compute a secret key, why should anybody else have a problem doing that, right? So it almost seems impossible, but it's actually not that hard to design key exchange protocols, and we will see how to do that. So key exchange was a problem introduced in the seminal work of Diffie-Hellman. This is a paper called New Directions in Cryptography, published in 1976. Diffie and Hellman later even got a Turing Award for this work. This work introduced the notion of basically digital signatures, public key encryption, key exchange, and so on. They were not able to actually construct public key encryption. We will see how to do that. El-Gamal and RSA did that at a later point. Okay, so what is key exchange? Let's try to define key exchange first. So a key exchange protocol, it's a protocol between two parties. So a key exchange protocol, let's denote it by pi, allows two PPT parties, Alice and Bob, let's just call them A and B. And note that private randomness is very important in a key exchange protocol, because obviously the only difference between a participating party and an eavesdropper is that a participating party has the private randomness using which it generated its messages, whereas eavesdropper can only just see the public messages exchanged. So RA and RB have, let's call these random tapes. So these random tapes are RA and RB respectively. To talk back and forth. So these two parties can exchange multiple messages with each other. So to talk back and forth in the following way. A and B generate a protocol transcript, let's call it tau. What is the protocol transcript? That's random tapes. So what's the protocol transcript? It's basically a record of the entire conversation. I send you some message, you send it back to me, you send me some other message, and so on. So we just concatenate all these messages, and that's your protocol transcript. So A and B talk to each other, they generate some protocol transcript tau. Now, what is the view of Alice in the entire protocol? View of Alice is everything which Alice has. So view of A, what is the view of A? It's the private randomness which she used. She obviously knows that, and she can obviously see the entire public transcript. And similarly, we have view of Bob is RB and tau, right? Bob doesn't know RA, and so on. And then finally, Alice and Bob output keys KA and KB respectively as a function of their respective views. Okay, so Alice will look at RA and tau, do some computation on it, and compute KA. Similarly, Bob would compute KB. And we basically need two properties. First of all, we need correctness. Correctness just says the following: probability, and the probability is taken over the choice of RA and choice of RB. Probability that KA equals KB should be just 1. Okay? So both the parties must agree on the key. If so, we just call it the key K. So at the end of the protocol, both parties can compute the key. What else we need? Adversary should not be able to compute the key. In fact, not only should the adversary not be able to compute the key must in fact look uniform to the adversary. So security says the following. For every PPT adversary Eve. So Eve is an eavesdropper. Eavesdropper just watches the communication. It doesn't actively tamper with the communication. So what is the view of Eve? Can anybody tell me what is the view of E in the protocol?
Just tau.
Exactly. Eve doesn't have any private randomness of any of the parties. Eve just sees all the public messages. And what we want is that given tau, the key K should look uniform. Okay? So we can express that in the form of computational indistinguishability. The key K and tau should look computationally indistinguishable from K and U size of the key K. Right? And I can expand this in a longer way, K comma tau, such that, you know, RA and RB are sampled at uniform, then tau is the output of the protocol pi, and then K is the output of Alice and Bob on tau and their respective randomness and so on. So we are just looking at the output of the entire experiment. Yeah.
Why are we replacing tau with uniform rather than K with uniform?
Sorry.
Yeah, okay.
Good point. Yeah, the key should look uniform, not the transcript. Alternatively, sometimes we don't necessarily want the key to be uniform, but rather a random group element. So in that case, what we would need is K and tau should look computationally indistinguishable from G to the power R comma tau, such that R is sampled uniformly from ZQ. Right, so when we are running the key exchange protocol, we can ask for keys of different format or different size and so on. So now let's try to build. Sorry. Now let's try to build. Let's try to build key exchange protocol. And we will see what Diffie-Hellman key exchange is and how it works. It's pretty straightforward, almost comes from the DDH assumption. So let's keep the DDH assumption in mind. Diffie-Hellman key exchange. So here we have a group G, and little g is the generator of this group. And again, the size of the order of the group G is, let's say, Q. And we assume that DDH assumption holds in this group. Then the key exchange protocol works as follows. So step 1, Alice samples some element X from ZQ. Okay? And Alice sends capital X equals G to the power small x. And by the way, again, let me state and even write that G to the power X really denotes G, it's really the group operation. It's not the standard multiplication. Whatever the group specifies, for example, in Sophie-Germain based prime order groups, it will be G to the power X mod P. Okay, so we will try to use the group in a black box way. It's just the group operation. Bob does something symmetric. So Bob samples, let's say, Y from ZQ, and Bob sends capital Y, which is equal to G to the power Y. Okay? So Alice and Bob set K to the power A equals K to the power B equals K equals G to the power XY. Okay? How do Alice and Bob compute this? For Alice, it will be basically Y to the power X, right? Alice receives Y from the other party. Alice has small x. So Y to the power X is G to the power XY. And KB equals X to the power little y, right? And both of these things are equal, just G to the power XY. So here is a very nice point, right? So this protocol allows you to compute the key if you had either this little x or little y. Either of them is fine. But if you have none of these, then basically it's not clear how to compute it. And in fact, we will show that DDH says that in that case, in fact, you cannot compute it. Right? So correctness is fine. Correctness is this basically. Now let's try to talk about security. Okay. So security says that Diffie-Hellman key exchange is secure, assuming DDH holds in the group capital G. And this is almost by definition. So what is the view? What is tau? Tau is just
Big
G
X,
to the
big
power
Y.
X and G to the power Y. Sorry, was there some question? So view of the adversary is just tau. Okay. Now, we know from the DDH assumption that given G to the power X, G to the power Y, G to the power XY. Okay. So this is just tau comma, sorry, let me write it here, computationally indistinguishable from G to the power X, G to the power Y, and G to the power R. Okay. But now note that the left side is basically tau and the key. On the other hand, right side is basically tau comma G to the power R, where R is a random group element. And this is exactly what we wanted. Let's look at this alternative definition of Diffie-Hellman key exchange. Right? So looking at the transcript, the key essentially looks like a random group element to the adversary. Okay, so very simple construction. Any questions? Okay, so now a very interesting question, which I hope you can answer. What about an active attacker? An active attacker can modify messages. Okay, an active attacker sits on the channel between Alice and Bob. They can receive messages from one party. They can change the messages in any arbitrary way before relaying them to the next party. And they can do that throughout the entire protocol. So against active attackers, so yeah, this is also called as man in the middle. So is Diffie-Hellman key exchange secure against a man in the middle attack?
No, sir.
No, why not?
So what I can do is like when say like you and some student were exchanging messages, so I captured both of your messages and send you two new messages, like to you and to the student also. So now you'll work with my keys. Since I know both of the keys, I can do stuff.
Okay, yeah, that's a good point. So essentially, the idea is that there can be a man in the middle who can run a separate key exchange protocol with me and another key exchange protocol with another student, and they will have both the keys. They can decrypt my messages as well as messages from the other student. They can see the messages, they can modify the messages, and so on. So can there be a key exchange protocol which is secure against active attackers? So this is actually impossible. And the reason for that is that Alice and Bob have never met. There's no notion of identities. So in that case, the following attack is always possible. So we have Alice, we have man in the middle, we have Bob. So Alice and man in the middle, they just talk honestly, right? There's no cheating required here. And then man in the middle has a separate session with Bob. And there's a key K here, key K prime here. So man in the middle just follows the honest strategy, and they will end up with a different key with Alice and another key with Bob. They will be in possession of both the keys, right? So later on, whatever message Alice encrypts and send to Bob, it will be under key K, which man in the middle has, can decrypt, read the message, then encrypt it under K prime. So Alice and Bob will have absolutely no idea that there is somebody sitting in the middle watching their messages, just decrypting and re-encrypting with the appropriate keys. Okay. So yeah, so key exchange protocols, they don't necessarily give you everything that you want. And we need something more. So later on, we will look at certificates and the HTTPS protocols using which you can establish a secure connection, even if there's a man in the middle. So there's a question, is there a significant delay? Not necessarily, this is all being done using computers. So yeah, it's almost instantaneous. So to continue moving on and eventually design a solution for secure communication, we need to look at public key encryption. In fact, public key encryption turns out to be somewhat more powerful than key exchange. So in their original paper, Diffie and Hellman were able to construct key exchange, but not public key encryption. They left construction of public key encryption as an open problem in their paper, and it was solved shortly thereafter. So we have seen secret key encryption. Now let's look at public key encryption. So here the idea is that there are different keys for encryption and decryption. The encryption key can be made public. Okay, so there are three algorithms.
Sir, so when
Just like secret key
Diffie-Hellman
encryption.
when Diffie-Hellman first came out with the paper and they just said that this problem is hard, like did the entire world just assume because they are saying it is hard, so they started working with that algo, like because till now we don't have any proof that it is actually hard.
So first of all, unless you resolve the P versus NP problem, there's no hope to prove that that DDH is actually hard. If you prove DDH is hard, that automatically implies P not equal to NP, right? Same for the factoring problem and so on. So yes, they did propose these problems. The community did try to solve these problems for a while. People are still trying to solve and break DDH, but 30, 40 years later, nobody has been successful. So that's really our only sort of confidence. And we can say the same for factoring. We can say the same for lattice-based cryptography, SHA-256, and so on. So almost all of cryptography is based on unproven assumptions. And that's inherent because until you resolve P versus NP, it will stay like that. Okay, so public key encryption has three algorithms. First is the key generation algorithm. Okay, key generation algorithm takes the security parameter as input. In fact, it really should be 1 to the power n, but let me skip that. And it's a randomized algorithm which outputs a public key and a secret key. The second algorithm is, of course, the encryption algorithm, which takes the public key and the message as input, and it outputs a ciphertext C. Then finally, and encryption is also randomized. And finally, we have the decryption algorithm, which takes the secret key and the ciphertext, and it outputs some message. Let's call this message M prime. Okay. Now, just like last time, we will require two properties. First is correctness, and second is security. Correctness just says that if you do everything correctly, then the message that you decrypt should be the same as the message that you encrypt with probability 1. So this should hold for every message M. What we need is the probability that decryption with SK of a ciphertext, which is encryption with PK of M. We are looking at the probability that this decryption gives you the message M, such that SK and PK indeed came from the key generation algorithm. So this probability should be 1. Now, what about security? It's very similar to secret key encryption, except that now the adversary is given the public key in addition to the ciphertext. So this is known as indistinguishability security for public key encryption. This is also called IND-CPA. There are stronger notions. I'll talk about them a little later. Okay. So this requires the following. For every pair of messages M0 and M1, for every PPT adversary A, the following should hold. Yeah, I don't even need to write here PPT A. Just we will require computational indistinguishability of ciphertext encrypting M0 from the ciphertext encrypting M1. Okay, so in one distribution, you are given PK and M0 ciphertext as well as PK, okay, such that PK-SK comes from Gen, and yeah, this should be computationally indistinguishable from the case where you are encrypting M1. Right? Pretty natural definition. Okay, and as always, we can talk in terms of prediction rather than computational indistinguishability. It's equivalent as always. So alternate formulation, same notion, IND-CPA. So here we choose one of these two messages at random. Adversary sees the ciphertext, and adversary has to guess which message it was. So we are looking now at the probability. So this is needed for every PPT adversary A. Adversary gets the public key, adversary gets encryption under PK of MB. Okay, and we are looking at probability that adversary successfully guesses B, such that, as always, PK-SK generated properly and B is sampled at random. So this probability minus half should be very close to negligible. Right? I can always output a random bit, but essentially that's what the adversary is restricted to doing. Any questions? So now let's try to look at, before we construct public key encryption, let's try to look at some of the basic fundamental properties of public key encryption. So what about randomized public key encryption? Should public key encryption be randomized or deterministic? What about one-time versus multi-time public key encryption, and so on? Okay, so let me give you a fact. So we saw deterministic secret key encryption. We saw it was bad, or really deterministic and stateless. We are just talking about stateless here. Now, what about deterministic public key encryption? This is actually a complete disaster. And why is that? Can somebody tell me why deterministic public key encryption is so bad?
If you want to distinguish, you can just encrypt the message because you have the public key and you can check if the encryption you get is equal to the one you're looking at.
Okay, good. So let me just explain you with the help of an example. Let's say the two messages are, let's say, attack or defend. Okay. And let's say my public key encryption is deterministic, right? I am the encryptor. I choose one of these two messages, either attack or defend, and I send the ciphertext over. Adversary can just decrypt the ciphertext without the secret key. How? Because adversary can encrypt attack, defend, and then compare a ciphertext with the two ciphertexts which he obtained. It's going to match one of them, and adversary basically knows what your message is exactly, right? So essentially what we are saying is, if message is either small or it has low entropy. Low entropy means the number of possibilities of the messages is small. Let's say polynomial. Then a PPT-A can entirely recover your message. And that's really bad. So that's why you would almost never see deterministic public key encryption. Having said that, deterministic public key encryption has been studied. It has its applications. So as an example, think about applications of deterministic public key encryption. If you're encrypting high entropy messages, deterministic public key encryption might actually give you something. So an example which I like is, let's say you want to encrypt a database, right? Encrypt, let's say not even a database, yeah, encrypt some text, one word at a time. Okay. Now, deterministic public key encryption will allow you to do search on this encrypted data. What you can do is, let's say I'm the server, I'm storing this entire encrypted text, right? The client comes to me, client says, hey, I want to find all instances of a particular keyword. Let's say I want to find all instances of Pittsburgh in the text. Then I, as the server, can just encrypt Pittsburgh, and I can just search it. I can just look for that particular string and then in the entire encrypted text. And then I can return all the instances where that encrypted text occurs. Okay, so even though it does weaken the security a little bit in encrypted search, it's actually very useful. And there have been some other applications of deterministic public key encryption.
Should I have a small question?
Yeah.
So like if I do something like this, that I always use deterministic public key encryption, but what I do is in my message I have a end word, and after that I pad it with random number of zeros, like say 5 lakh zeros or 5 crore zeros, and then I send it. And like, so because like earlier we said that like because the space is so large, like the adversary can't compute all the messages. So then also I'm safe, right? If I use the deterministic public key encryption, but I pad myself with random number of zeros, or like a lot of zeros.
Well, maybe not random number of zeros, but random number. That's what you are saying. I mean, if it's a random number of zeros, I can maybe look at just the size of the ciphertext and I can figure out how many zeros there are, and I can just try.
Okay. So random number, a big random.
Yeah. Yeah. If you encrypt, if you pad it with a random number, then that's not deterministic public key encryption anymore.
Why? But my message is like encrypted using public
So
deterministic
what
public
you're
key.
saying is we can try to convert a deterministic public key encryption into a randomized one by modifying the encryption algorithm to generate a random number and append it to the message. So any encryption which samples a random number and uses that in the ciphertext, that's not deterministic, right? So yeah, what you're saying is you can convert deterministic to randomized. So yeah, something like that might work. Depends on which encryption scheme we are using.
Okay, I see.
Okay, good. So another question is about one-time security versus multi-time security. And here's a very nice fact about public key encryption. As far as public key encryption goes, one-time security is actually equivalent to multi-time security. So let's say we have one-time secure public key encryption is also let me call it multi-message. One message and multi-message. Okay, we didn't even define multi-message security. Let me do that quickly. It's a simple generalization. Okay, multi-message secure public key encryption. Let me actually erase it and I will use this space for the proof. Okay, so this is multi-message security. So we have two message vectors, as you can expect. So we have a vector M, let's call it MI0. And we have another vector M1I. Okay. And now adversaries either give an encryption of all the messages here or all the messages here. Given the public key, they should look computationally indistinguishable. So essentially, encryption under public key of M0I, okay, for all I, and the public key such that the keys are generated honestly. This is computationally indistinguishable from the case when we encrypt the other message vector. Okay, the definition is the definition clear? And now the situation actually is very different from symmetric key encryption. In symmetric key encryption, we had one-time pad, which was only one-time secure, but definitely not multi-time secure. We had other constructions of multi-time secure symmetric key encryption. Fortunately, in public key encryption, once you construct something with one message security, it's also automatically secure with multiple messages. So let's try to prove it. and we will use a generic hybrid argument again. The reason why this hybrid argument works when the same thing doesn't work for symmetric key encryption is because now you have the public key and you can encrypt messages publicly on your own. And that plays a very crucial role here. So we will construct various hybrids. Hybrid 0 is just the first message vector and then the public key. Okay, hybrid 1, we start changing messages one by one. So hybrid 1 is encryption, M11, okay, but the rest of the messages are the same. M0I, I is greater than or equal to 2. Okay, keep going. And finally, you have HK, where the first K messages are coming from the second vector, M1I, where I is less than or equal to K. And then you have M0I, I is greater than or equal to K plus 1, and then finally you have the public key. Okay, and eventually you will have the encryption of the second message vector entirely. So these are our hybrids, and we will prove that hybrid K minus 1 is actually computationally indistinguishable from hybrid K for all K. Okay, any questions about the proof structure? And again, here the basic idea is that what is the difference between hybrid K minus 1 and hybrid K? It's just the Kth ciphertext, right? The Kth ciphertext either comes from the first message vector or the second message vector. So we will take it from outside from a challenger, right? And we will try to distinguish if it's an encryption of MI K minus 1 or so which messages are different? Let me write them down. Difference is in either it's in hybrid K minus 1, it's MK0 versus MK1, right? In the kth position. So now let's say you are given an adversary, PPT-A, to distinguish HK minus 1 and HK. We will build PPTB to distinguish encryption of M0K from encryption of M1K. Okay? Because that's essentially the only ciphertext which is different. How do we do it? Why does it work only in the case of public key encryption? So here the idea is that B takes a ciphertext C as input, and B has to determine, is it this or is it this? Right? So B places C in the kth position. And now here comes the crucial point. For all other positions, B uses the public key to prepare ciphertext on its own without the help of any challenger, any external party. Okay? And now if C was, let's say this, then this is hybrid HK minus 1, otherwise it's hybrid HK. So if A can tell you which hybrid this is, then B can tell you which ciphertext C was, which breaks the one-time security of public key encryption. Okay, so this basically completes the proof. Any questions? This can't work for deterministic public key encryption. Yes, that is correct, because the reason is that for deterministic public key encryption, you can't even have one-time security. Given a ciphertext encrypting one of the two messages, I can immediately tell which one it is. So now let's try to build public key encryption. And again, we will use the DDH assumption. So we will see what is known as El-Gamal public key encryption. So Diffie-Hellman, they published their paper in 1976. They were stuck on building public key encryption. They left it as an open problem in their paper, even though they did have this, this key exchange protocol. Then later on, like 2 or 3 years later, RSA came along. It was in 1978, I believe, that RSA was proposed as a public key encryption system. Then finally, El-Gamal came along only in 1985. So basically 9 years after the original Diffie-Hellman paper. And you will be shocked. El-Gamal public key encryption is actually almost the same as Diffie-Hellman key exchange. So what we will see is that there's already a public key encryption system hiding in Diffie-Hellman key exchange. The idea is basically you look at the first message as the public key, and you look at the second message as sort of the ciphertext. And that was basically the entire insight which El-Gamal had. So sometimes, very smart people can think about a problem for like 9 years. Stupid solution, maybe they can't see it. So essentially what we will see is that any 2-round key exchange actually implies public key encryption. Okay, so let's write down the Diffie-Hellman key exchange. So this was Alice sends a message g to the power x, Bob sends a message g to the power y, and then use g to the power xy to encrypt. Now, again, coming to key generation, and here our security parameter is q, because q is the size of the group. So again, let's assume you have G, capital G, this is the generator, and order of capital G is Q. So now your key generation works as follows. So again, sample X at random from ZQ. Your secret key is just X. Your public key is G to the power X. Okay, so the first message essentially serves as your public key. How do you encrypt? So let's say I have a message M, and by the way, the message M must be in the group G. So you can encrypt any group element. So let's say sample Y, again from ZQ. Okay, actually let me call it R rather than Y. And then your ciphertext is just G to the power R, okay, which is the same as this message. Then finally, I do want to encrypt the message. I obtained the key G to the power X and XR. And then I just multiply my message with it. Okay, and the idea which we will see in the proof is that if G to the power XR looks random, then even M times G to the power XR looks random, a random group element. So this is essentially your ciphertext. And let's call this C1 and C2. So ciphertext has 2 components. Let me call the ciphertext just C. So the decryption algorithm takes the secret key and the ciphertext as input. How would this work? So first, the decryptor has to compute the shared key G to the power XR. Okay. So first you compute C1 to the power your secret key. Okay, and this will essentially be G to the power X R. Okay, and then you output C2 times the inverse of this, C1 to the power minus Sk. Okay, and this will essentially be m times g to the power xr. I don't know why I keep writing y. G to the power minus xr. So this is just m times g to the power 0, which is the identity element. Okay, so correctness is good. Any questions? So now let's try to prove security. And remember that because we have already shown one-time security implies multi-time security, we only have to show one-time security. That's the nice thing about public key encryption. So security says the following. El-Gamal public key encryption is IND-CPA, assuming DDH holds in the group G. So what do we need to do? We basically need to show the following. Encryption of the message M0 such that PKSK comes from Gen looks computationally indistinguishable from encryption of M1. Right, so now let's consider the following sequence of hybrids. Hybrid 0 is, so what is encryption of PK comma M0? It's, so let me write, oh, I missed the public key here. And also on the right side, we have the public key. So you have the public key and the ciphertext. Now let's look at the hybrid 0. Hybrid 0 is just the public key and the encryption of 0. So the public key is just g to the power x, and the encryption is g to the power r, comma m0 times g to the power xr. Okay, and let me skip this part. This is everywhere. What is hybrid 1? Hybrid 1 is g to the power x, g to the power r, and finally m0 times g to the power z, where additionally z is from zq. Hybrid 2, g to the power x, g to the power r, and g to the power z. So no message here. Hybrid 3, g to the power x, g to the power r, and m1 times g to the power z. Z is random again. Then finally we have our last hybrid, which is g to the power x, g to the power r, and m1 times g to the power x r. Okay, and note that this is the left hand side and this is the right hand side. So if you can show that all these hybrids are indistinguishable from each other, we are done. So what is the difference between hybrid 0 and hybrid 1? I'm just replacing this g to the power xr by a random group element. Okay, so hybrid 0 is computationally indistinguishable from hybrid 1, and this directly follows from the DDH assumption.
So does this follow from the fact that M0 will always have the inverse in the group?
No, not necessarily.
Because if you're given M0 into g to the power xr and M0 into g to the power of z, then you can multiply them with M0 inverse. So if you can distinguish between two of them, you can distinguish between them. That's what I thought.
Yeah, you don't need that here. We are essentially using the fact that if two distributions are indistinguishable,
Oh, okay. Then A of x and A of y will vanish.
then even any PPT function is also indistinguishable.
Okay, thank you, sir. Thank you very much.
Okay, because if I'm given g to the power x, g to the power r, and g to the power xr, I can multiply m0 to the third component on my own. Okay, is this clear? Any questions? Now my claim is H1 is actually identical to H2. And here we will use the fact that G is a generator essentially. Okay, so since G is a generator, it means that M0 is equal to some G to the power, let's call it Z0. Okay, now what is M0 times G to the power Z? This is equal to G to the power Z plus Z0. Okay, and now my claim is basically Z to the power Z, where Z is uniform from ZQ, is actually the same as G to the power Z plus Z0, where Z is sampled from ZQ. And this should hold for every Z0. Okay. Essentially, what I'm saying is I sample some random element from ZQ, or I sample a random element and then add something fixed. It's the same distribution. It gives you the same random element. Okay, so this proves that H1 and H2 are the same, essentially. Is this clear? And then finally, what about H2 and H3? H2 and H3, again, they are identical. Here I have G to the power Z. Here I have M1 times G to the power Z. Both are equivalent to a uniform group element. Then finally, what about H3 and H4? They are computationally indistinguishable. And that follows from the DDH assumption. Okay, so this is basically a proof that El-Gamal is a secure public key encryption system. So we don't have time to start RSA. We will do that next time. Let me end with some comments about the security. Okay. So people have considered various stronger notions of security. So here, what was the adversary given? In IND CPA, adversary is given public key and a ciphertext. So there are stronger notions like IND CCA, even their variants. There's something which is known as CCA1, CCA2. And here the idea is that adversary is given public key and ciphertext and decryption of several ciphertexts of adversary's choice. Why do we do that? So let's say you are an unsuspecting party. Adversary keeps sending you many encrypted messages, you decrypt them, and based on them, you reply to the adversary, right? So the point is that now when I reply to the adversary might actually know what the decryption was. So adversary prepared the ciphertext without potentially knowing the decryption. I decrypt it, I send my reply. That might leak some information about what the message inside the ciphertext was. So adversary might essentially trick me in some sense to decrypt several ciphertexts which it prepared. And potentially that might leak additional information, right? So this is known as the CCA, chosen ciphertext attack. Adversary chooses the ciphertext and uses that somehow in attacking me. And we know of public key encryption systems which are secure even according to this definition. El-Gamal is not secure according to this definition. You need to do some more work to convert El-Gamal to get CCA security and so on. So the point is that IND CPA security is more or less like the starting point rather than, you know, the gold standard of public key encryption security. Okay, so we will stop here for today, and I'm happy to take questions.